projections and work. Let's start off by finding work given two vectors. We'll define work as force times distance, which is the official definition of work. And suppose we have two vectors. One is force, which I'll label here, and the other vector is labeled d. So we could consider that distance, but really we should think of this as displacement, a change in distance. So a displacement vector. And so if you want like a real world context, imagine that somebody is pulling a wagon. And this is the handle, and they're pulling the handle at an angle, so their force is going not directly down the line, but up at this angle theta. However, the wagon is going to go along this horizontal path, or along this displacement here. And we want to find the amount of work that is done. So we're going to use a little bit of trig and a little bit of dot products. So a quick reminder, when we were doing the dot product video, we saw that if we have two vectors A and B, that equals the magnitude of A times the magnitude of B times the cosine of the angle between them. And we'll come back to that in just a little bit. So let's look at our picture once again. So even though we have a force which is going at an angle, we want to calculate the force that's in the direction of our displacement vector. So when we say force, we're talking about the actual force in the direction of the distance we're going. So how big is this vector right here? We can consider this the amount of force in the direction of D. Well, from right triangle trig, we see that the cosine of theta equals, and I'll put like Fx for the force in the x direction, is the magnitude in the x direction over the total magnitude of the force. In other words, the force that we want, the force in the x direction, its magnitude is F, that is magnitude of the actual original vector F, times the cosine of theta. Now, how far did we pull? So even though I drew the arrow here, we could have pulled any distance along this line D. And so the distance we pulled, that is the displacement, is going to be the magnitude of D. So our work is going to be force, the force in the x direction, that is magnitude of F cosine theta, times the magnitude of our displacement vector. Rearranging a little bit, and using this fact up here, we see that our work is the dot product of force times displacement. So let's do an example here. Suppose we have our force vector is given by 70 cosine 35 degrees I plus 70 sine 35 degrees J. So if we were to draw a picture, our force would be 70 newtons, and our angle would be 35 degrees. And let's assume we're going to a pole in the x direction. So let's say our displacement is 100I plus 0j. So displacement only in the x direction. Then the work done is the dot product of force with displacement, which is going to be 70 cosine 35 times 100 plus 70 sine 35 times 0. And we get approximately 5,734 Newton meters, where Newton is the standard unit of force. Well, let's go and talk about this idea of projections. I already drew a projection, but I didn't talk about it formally, and we want to do that now. So let's consider two vectors. In this case, the vector in the horizontal, and it does not have to be horizontal. This is just to make the concept a little bit easier when we're learning. We'll call that vector A, and the vector at the angle we'll call B. Now, imagine a light source, like directly above the vector A, that's shining down on B, so that B casts a shadow onto A. So this vector here I'm going to call U. And we call that vector the projection of B onto A. And I'll write it out in words. The projection of B onto A. And just to make it intuitive, I like to think of it as a light source, where this projection is the shadow that's cast onto the other vector. Now, my claim is that this vector U, that is the projection of B onto A, is given by the following. It is A dot B over the magnitude of A squared times the vector A. So it's really some constant times the vector A. Of course it is. So this projection is directly along the same path that's parallel to the vector A. And it's just some multiple of A. It could be a portion of it, like this looks like about a third of A. It could be 2 times as big A, it doesn't matter. But it's some constant times my vector A. So let's prove that, because in this course we want to start to learn how to prove things a little bit more rigorously, especially if you haven't done this before. So how could I prove that this is true? Well, there are a couple steps. Let's look at the first step. We saw it when we were doing the work, when we were setting up. We could see that the magnitude of U is going to be the magnitude of B times the cosine of the angle. That's strictly from right triangle trig. Now, I also know, since U is some constant times the vector A, it's also some constant times A over the magnitude of A. So what did I do here? So I'm going to change it from being kind of general to being something a little more common that we use. Recall that A, that is the vector A over the magnitude of A, is a unit vector in the direction of A. So I'm simply saying U is some multiple of 1, really, right? For example, And we're not looking at A anymore. We're going to look at this unit vector A. You know, U could be 1/2 of this unit vector. Which of course means that the magnitude of U is 1/2, right? Because the magnitude of this portion is always 1. Or U could be 2 times A over the magnitude of A, which would mean that the magnitude of U is 2, right? So in general, we can say that U equals some number times A over magnitude of A. But that some number is always going to be the magnitude of U. Something like that. So let's put another piece together. Which is, since U, and I'm going back to number 1, but I'm going to add some stuff. Since U, the magnitude of U, is the magnitude of B times the cosine of theta, and we know that the cosine of theta is A dot B over the magnitude of A times the magnitude of B, we could write the magnitude of U as magnitude of B times this version of the cosine of theta, A dot B over magnitude of A times the magnitude of B. So the magnitude of a vector is a number, so those will cancel out. So we get that the magnitude of U is A dot B over the magnitude of A. And now if we put this together with what we found in part 2, we get that the vector U is the magnitude of U, which is A dot B over the magnitude of A, times A over the magnitude of A. So dot products are numbers, magnitudes are numbers, and this A over here is going to be a vector. So we get A dot B over the magnitude of A squared times A, which just means U is some multiple of A, which is kind of where we started up here when we're doing the claim. Let's do one example. Let's find the projection of B onto A, given the following. A is the vector -2, 3, 1, and B will be the vector 1, 1, 2. Well, I know that the projection of B onto A is going to be A dot B over the magnitude of A squared times the vector A. So A dot B is going to be -2 times 1 plus 3 times 1 plus 1 times 2 all over the magnitude of A, -2 squared plus 3 squared plus 1 squared, and then all squared times the vector A. And simplifying all this, we get the projection of B onto A is 3 over 14 times the vector A, -2, 3, 1.